Please welcome our next speaker, Jennifer Porter. Jen is a MinEx CRC embedded researcher, who's nominally from University of South Australia, but working with us. And she works in the Regional Geoscience Directorate of GSWA.
Hi everyone, I'm the last thing standing in between you and coffee. So let's talk about apatite, specifically how you can tell information about fluids from apatite, and even more specifically, hopefully, what kind of mineralization, if there's mineralization, and what kind of mineralization you can understand from analyzing apatite. So here we are again revisiting the gap. If you haven't understood anything about the gap from previous talks today, we don't understand much about it. We don't have much information. It's undercover, sometimes hundreds of meters undercover, very little bedrock exposure, and very few drill holes that reach basement. On the very eastern edge of the gap, we have the western Arunta region, which Aaron nicely explained to you already. It's comprised of two terrains, the two Paleoproterozoic terrains, and they are separated by this giant craton scale feature, separating North from South Australia, and the rest of the area is covered by basins of varying age, including the Canning Basin off to the west side here, which is covering up a potential another giant shear zone called the Last-Year Shear Zone, which may represent the boundary between the Western Australian Craton and North, to be determined. So one of the main features of this area is that it's completely surrounded by these giant shear zones, which can provide fluid pathways. So if we understand this terrain better, we may be able to also identify mineralization and target that mineralization better. So why are we using apatite? When you're in an area that you don't have much rock, not much bedrock, and few drill holes, and you're going to study one mineral, you want that mineral to exist in those rocks. And apatite is that mineral. It is found in most rock types. So it's ubiquitous. But more importantly, it's calcium phosphate that contains within its structure halogens. And halogen content and chemical characterization can be used as a proxy for the fluids that formed that apatite and therefore the rock that apatite's in, or the last hydrothermal event that touched that apatite and affected it. So halogens include fluorine, chlorine, but less commonly, or in a less amount, bromine and iodine, but it also contains water, hydroxyl, OH. But I'd also like to point out that chlorine is one of the major ligands that moves metals in hydrothermal environments. Other things incorporated within the apatite are rare earths, other trace elements, which multitude of researchers have been using to identify provenance, where the fluids or the rock came from, but also whether or not it's found near mineralization and what type of mineralization that could be. And on top of that, it also incorporates radiogenic isotopes, which can be used to date that apatite and potentially date that mineralization. And if not, it'll give you information on terrain evolution. That's just a cartoon demonstrating that fluids are found throughout at every stage of a mineralizing event, from the source of the fluid, picking up chlorine or another ligand that can move your metals, pick up those metals, and deposit it at various stages along the way. So we're looking at gaining a more holistic information about a mineralization system from a source, the processes acting on it, and how it deposits. And conveniently, apatite can contain elements from each of those stages. What a useful mineral. So what are we doing practically? From those drill holes that you saw on the map, we have, we're taking samples that are obviously affected by fluid and obviously not affected by fluid. And for example, on the left-hand side from the top-up rise area, which is in the Lassiter shear zone. We go from a biotite gneiss. Within a meter later, we have a rock that is 50% quartz and 50% sulfides, including iron sulfide and iron copper sulfide. So we're going to sample apatite from this area and that area, characterize potential fluid that formed them, and every stage in between, how it changed. So that's a meter scale. We're also going to look at thin section scale. Here we have a dolerite, not diorite, that has been completely transformed into K feldspar and a calcite vein. We're sampling individual apatites around from the vein outwards. So, preliminary results. This is another thin section that is amphibolite. The green is amphibole. The dark purple is plagioclase, and we have a rather dramatic vein cutting through it that's made of calcite and with alteration of K feldspar. I don't know if you can see there's yellow dots, and each of those yellow dots represents an apatite that we have sampled, and I have plotted up the fluorine content in red and the chlorine content in blue from 0 distance away from the vein to 20 millimeters. And what you can see there is there's not much of a systematic change away from that vein on that scale using composition. However, last week I was looking at stable isotopes of chlorine, and preliminary results suggest you are able to see a systematic change in stable chlorine isotopes where you can't see change in weight percent, but that's preliminary to be determined. On a drill hole scale, these are each of the drill holes. Each of these colors represent a drill hole within the West Arunta region, including the blue series is the top-up rise holes, which is in the Lassiter shear zone in the far west side of the area. And you can see that most of apatite compositions from each of the drill holes are actually quite fluorine-rich, so we have fluoroapatites, but most importantly, the one that is chlorine-rich is top-up rise 4. You can see it's most chlorine-rich here, and you can see it also chlorine and water-rich there. Top-up rise 4 happens to be the drill hole that is furthest into the Lassiter shear zone, perhaps giving an indication that there's a more hydrothermal fluid activity in that particular rock. So what we'll be doing is investigating more of that series of drill holes along the Lassiter shear zone, as well as along the Central Australian shear. So we would like to collect more information on drill holes, different rock types within the drill holes, get a baseline of rocks that aren't affected by fluids, get different types of fluid events, quartz veins, as well as calcite veins, as well as pyrite veins, and use previous researchers' discrimination diagrams, for example, using halogen ratios to identify whether or not you might be near a mineralized zone, what type of mineralization is it, as well as gain terrain information using other discriminants, normal trace elements, identifying what kind of metamorphic history the rock has gone through. Important for this area as it's not well understood and not very well studied. And that's the future plan.